Hey guys, Mr. Ye here, and we're going to be looking at section 2.5 from our textbook today, which deals with scatter plots. Now, you very well might have seen this before in other classes, in science classes, when you're graphing results of an experiment, for example, that's a common one, in other math classes. But we're going to go through not only how to make a scatter plot and what all those dots mean, but how to use that data, use that information to write an equation that models whatever phenomenon we're plotting, and use it to predict a future value. So that is what we're doing today. So to start, what is a scatter plot? A scatter plot, as you can see from the screen, it's a set of ordered pairs. We know that word set. We know ordered pairs are just XY points. So it's a set of ordered pairs in the coordinate plane. And scatter plots are usually used to map a couple different quantities that we are interested in comparing and seeing if they have an effect on each other. So for example, this scatter plot of mpg, miles per gallon, versus weight. So seeing if there's a trend with lighter vehicles or heavier vehicles having better mpg, maybe, better mileage. And so right here, you can see just by looking at it, there does seem to be some sort of pattern. And it's not perfect, and maybe I drew that line too high, but it does look like the lighter the weight of the lighter the vehicle, the lower the weight of the vehicle, the better mpg it gets, the better mileage it gets, and it's more gas efficient. Well, that makes sense because it doesn't have to propel as many pounds, as much weight, and so you can get more miles out of it because it's a lighter vehicle. Whereas if you have a really heavy vehicle, it often doesn't have great mileage, and you can see that down here. The really heavy vehicles are not getting very many miles to the gallon. So this is something that becomes kind of obvious when you look at all this data on a graph. Does it hold perfectly true for every vehicle? No, not necessarily. This guy right here that I'm going to circle in green is pretty heavy, but gets decent mileage, it looks like. So there are exceptions, of course. The same way that there might be, I'll circle this next one in blue, really light vehicles that don't get great mileage. But in general, we can say there is a trend that the heavier the vehicle, the fewer miles per gallon it gets. What about this one? Revenue versus customer satisfaction is what that title says. And so you can see kind of the opposite trend. This one looks like it's definitely going uphill, which makes sense. Customer revenue is plotted on this x-axis. So if a business is making lots of money, that's what revenue means. If they're bringing in money and customers are paying for things, then customers are probably having a good experience or liking their products, which means customer satisfaction is high. So when customer satisfaction is high, they'll buy things and they'll probably come back and they'll probably tell their friends. Whereas if they buy something and they don't have high customer satisfaction on that very left-hand side of the graph, maybe they don't come back. They have low customer satisfaction. That means less revenue for the business in question. And so this scatter plot also illuminates a trend that makes a lot of sense when you think about it. And that is kind of the point of scatter plots, is to be able to illuminate those trends and see those patterns. So another piece of vocab, I'm gonna color code this, that we need to talk about is correlation. Correlation means these two quantities are related somehow. Now, a positive correlation is really easy to identify because it looks like a positive slope. Remember, an uphill line has a positive slope. So this is called a positive correlation. In other words, when one quantity goes up, the other quantity goes up. They do so together. And so a positive correlation, you can just remember as it looks like it has a positive slope, an uphill line. Versus a negative correlation, which looks like a negative slope, downhill line. As one quantity goes up, and I'm trying to figure out where to draw this, as one quantity goes up, the x's are going up, the y's are actually falling, going down. So it's a negative correlation, and it looks like a downhill line, negative slope. And then kind of a fun one, What about just no correlation at all? You look at that third scatter plot down there, and those dots, it doesn't seem like they're going uphill with any discernible pattern. It doesn't seem like they're going downhill. It seems like they're just there. They're just splattered across that coordinate plane. So no correlation. There's no real pattern that we can find. And sometimes that's really good information, that there's no pattern we could find. So before we get to our problem, and we're really only working one problem today because these are somewhat extensive and I want to make sure we have time to talk through it really thoroughly. Two other pieces of vocabulary: a line of best fit. And you can see its definition on the screen there, a line that approximates the correlation of the scatter plot. So kind of like I was doing very roughly earlier, just drawing a line in, that's basically what a line of best fit is. It's an approximation, and we try to draw it as best we can so that it's modeling the data. You can notice this one rule of thumb some teachers say is make it so half the points are above the line, half the points are below the line. That's a very simplistic view of it, but it's not bad advice. Trying to draw a line just through those points. We can see this one does have a little bit of a positive correlation, it looks like, but it's not very well defined. You know, they do seem to be going uphill gradually, but there are lots of exceptions. But that information is good if you're studying this phenomena. And the last thing that we do is once we have our line of best fit, we're going to be writing prediction equations. And so what is a prediction equation? It's an equation for this line of best fit. And it's an equation so that we can then predict, okay, this graph goes up to x equals 11. What about x equals 20? Where would this line be? And we can predict future values. We can predict larger values, whatever we need, so that we can make use of our analysis of the data. So here's the setup. As you can see, we got a table of information: year, 1994, 1996, every 2 years it looks like, and then price in the thousands of dollars it looks like, so 130,000, 140,000. Now, I stole this data from our textbook, and it has to do with the median real estate price in each of these years in a certain area. What was that median home price in these years? Well, that's great, but we're not living in 2004 or 1996. I want to know if this trend continued, what would I expect the median home price to be in the year 2020? So here's how we're going to do that. We're going to plot these points on a scatter plot. We're going to draw our line of best fit, find our prediction equation, and then use that prediction equation to predict the value that would be associated with the year 2020. So as you can see here from my graph, I've already kind of started a couple things. On that y-axis, that left-hand side, I put a break in the graph. That's what those two double bars mean, because I didn't want to have to graph 0 to 80. There were no median home prices in that $0 to $80,000 range. So I kind of just wanted to start around 80. And so I'm going to start numbering this, and you can see I've made every 2 lines 30,000. So this will be 140. Again, notice that I labeled this in the thousands just so I don't have to write as many zeros. This will be 170,000. This will be 200,000. This will be 230,000. Now, how did I know to go by 30,000 every 2 lines? I looked at the problem and, you know, before class, before I started this video, and kind of just figured that out. So sometimes you'll have to make that judgment call, so you're not using an entire sheet of paper for a single problem, unless that's your intention. Now, what I want to talk about on the x-axis is really important here. This is going to make your life way, way easier. Notice that my x-axis is not just years. Specifically, it's years since 1994. Why would I do that? Why would I say years since 94? 2 reasons. One, why 94 specifically? Because that was the very first item in my table that I have information about. But the biggest reason is because now I can call that 0. I can call that 0, which is going to make our lives way easier when we're finding this equation. Years since 1994, well, 0 years since 94 would be basically 94. And then 2 years since 94 would be 96. And I'll just keep going 4, 6, 8, 10, 12. And I won't write every year in parentheses below, but hopefully you can see years since 1994. I'll do one more. This will be 98. 4 years later. So in this way, we now have a coordinate plane kind of set up to plot these values. I'm going to plot them in green. So 1994, 0 years since 94 was $130,000. So that's going to be right around here. 96 was $140,000. So that one's exactly on that last point. 98 was 152.5. So almost to that 155, right about there. 2000 was 169. 2002, 187.6, 187.6, right about there. And then 2004 was almost 220. So I'm going to put it right about there. Notice that these graphs, these scatter plots can be, again, somewhat approximated because when I'm jumping by 30,000 every 2 lines, so 15,000 every 1 line, at some point I'm just going to have to put a point in there and hope it's about right. So plotting the scatter plot, you've probably done this before, not too bad. I need to draw my line of best fit now. And I need to decide, where is that line? Is it right here? I don't think so, because it seems like it's going up more at the end. It seems like that slope is like getting steeper and steeper. So I might draw my line maybe right about there. And this is where all of our answers can be different, because we're all going to draw slightly different lines, and that's okay. I'm going to draw my line on my ruler and look at it and make sure I'm happy with it. Does that line kind of model the data? I'm pretty happy with it. There's definitely a positive correlation, so a positive slope, and it looks decent. So we have our scatter plot, we have our line of best fit. The question now is, how do we write our prediction equation? So our prediction equation will typically be in the form, the slope-intercept form. And what I need to do is I need to find 2 points on my line that I can approximate. And so I'm looking for 2 points that are kind of near lattice points or right in the middle maybe. So I see one that looks really good right here. And if you look, and I'll zoom in, if you look, that one hits almost exactly on that lattice point. So that point was 2, and then 15, so 2, 125, because that's right in the middle of 110 and 140. So 2, 125. And I don't see another one that hits like perfectly, so I think maybe I'll look at this one, which hits just about in the middle there, between those lines on that y-axis. So I'm going to call that 192, because this would be 185. So right in between 185 and 200, just about 192. So what was the x coordinate? 7, 192. Again, our answers will be a little bit different, but that's okay. What's cool now, though, is that I have 2 points. What can we do with 2 points? Well, I can find the slope of my line, y2 minus y1 over x2 minus x1. So I'm going to do that. I'm going to say 192 minus 125 over 7 minus 2. And so if you need a calculator, go ahead and grab your calculator. This looks like 67. Oh gosh. Looks like 67 over 5. And so I love fractions. I'm going to leave it like that. M equals 67 over 5. 13.4. So it's saying every year that median home price is growing by about 13,400 according to my line. Can I write a slope-intercept equation from this? The answer is yes, actually, because I have my slope and I have a point, right? I can use either one of these points. I'll use the one with smaller values just to make my life easier. But if you remember from last section, we said we can start in point slope and we can translate that to slope intercept pretty easily. And so what I just did here is I wrote out my y minus y1, that 125, equals m, which I just calculated, times x minus x1, my x coordinate from that point. Let's put this in slope intercept form. So that means y minus 125 equals 67/5 x minus 134/5. And you might need to use a calculator for that. And so I've got my calculator out right now. And it's not going to show up on the screen, I don't think. Nope, it didn't. But I can go, what is negative 134 divided by 5? So that's about negative 26.8. But then I'm adding the 125 from the left-hand side, 98.2. So I'm going to turn that into a fraction because I already said I love fractions. 491/5. So y equals 67/5 x plus, and according to my calculator, 491/5. That is a fantastic prediction equation. Slope intercept form. And here's the best part is now we can plug in any x value and we will find where it lands on this line. So think back to the question that kicked this all off. The question that kicked this all off was, what will the median home price be in this region if this trend continues in the year 2020? So I just need to figure out what x value to plug in. We said that this x, 1994, x equaled 0, because we did years since 1994, 2 and 4. And so you notice the pattern. It's just whatever year, 2000, for example, minus 1994, that's how we get our x coordinate. So I'm going to use that. I'm going to say, what is 2020 minus 1994? And that looks like 26 years. So x equals 26. I just need to plug in x equals 26 into my prediction equation. And let's see what we will get. X equals 26. So y equals 67/5 x, which was 26, plus 491/5. And really, honestly, guys, I'm just going to pull out my calculator for this. 67/5 times 26, and then add 491 divided by 5, and we get 446.6. 446.6. 446.6. So what is that saying? Well, that's saying that the median home price in 2020, if this trend continues, would be like almost $450,000. Does that seem to work out? Yeah, I mean, it seems like it's going up pretty rapidly. In 10 years, it went up by $90,000. So in another 10 years, it'll go up by even more because that rate of ascent, that slope is getting even steeper based on those green dots. So I would say this seems reasonable. This seems reasonable that it could be $446,600 there for our final answer. Now, something that I need to mention. You could get an answer that's way different. What if, when you were drawing your line, I'll draw this one in dark purple. What if you had said, that's not really the slope is more like this? Because I think that jump at the end was a fluke. What if you drew that dark purple slope? Well, then you're going to get a much lower value, right? Because it's not growing as quickly. So 2020, it won't be as high. If you have all this work on your screen, If you've worked it out, found the slope, found those 2 points, found your prediction equation, and you got $320,000, great. I don't care that it's 100,000 off. As long as your line looks like it could model, it's decent. It's an approximation, remember, and you have all the work supporting your argument, you will get full credit for problems like this. Obviously, we want to draw our line as best as we can. I don't know that mine was originally, because it started out definitely not quite as steep, these green dots, but then it looks like they're starting to shoot up a little bit. So that's why I made mine a little bit steeper. But guys, that's the process. That's how you can use some of this linear equation stuff we've been talking about, these different forms, and write equations that actually reveal things in real life, in science or in real estate or economics, taking data, finding the trend, and then writing a prediction equation so you can predict future values. So guys, that is it for this section, 2.5 scatter plots. I know we only did one problem, but they're kind of extensive. So hopefully you saw that and it kind of made sense and you were following along. And so you'll be able to do this in your future. Until next time, have a good one.